Section 12.2. So in this section, we are basically looking at linear regression again, but we're looking at examples where when we originally plot the graph, it does not appear to be linear. It might have some kind of a curve. And so this right here is what we refer to as the ladder of power. And so if you look at this situation, we've only been doing problems where our power was a 1. So we had things where they were right away making something that was linear. But sometimes we have to transform either the X list or the Y list. And by transforming that, we can end up with a new graph that is linear, and then we can write a new equation. Maybe it's a quadratic, or maybe it's a square root, or maybe it's a reciprocal, whatever kind of situation. But we might also have something that deals with logs, and logs are extremely popular. The common log, which is base 10, and the natural log, which is base E, and they describe many curves that we want to try to create a model for. They're probably your most important go-to models, and they are the model that's being used to model COVID-19. So, for example, when you're trying to decide what you want to do, if you see things that are increasing exponentially, then probably a log is going to be involved in transforming that data. If you see things changing by orders of magnitude, like going from a 10 to 100 to 1,000, that's a very good estimate that you're probably going to be using logarithms. Now, to do any of this, it's basically going to involve guess and check. And so you're going to do a transformation, you're going to run your linear regression, you're going to look at the R and, check the graph and decide if you feel like that was the best one. So I'll do an example like that. My first example. I've divided this into 3 examples in 3 different videos. So anyway, so your calculator can also do exponential regression and power regression. And so those don't help you find the residuals. However, and I probably should have told you this years ago. Well, not years ago. We've only been together. The calculator actually finds your residuals automatically. If you look in the, if you click on the button, second stat, and look at the lists in there, there's actually one that's called resid, and they actually find the residuals for any linear regression that you do. They are automatically, but the thing is, at least you know how to find residuals, Anyway, so we'll use that to make our life go a little bit faster, or a little easier. So anyway, helpful properties of logarithms. Hopefully you remember things about expanding and condensing your logarithms, and remember things like how you can bring that power out in front of a logarithm. So we'll be using that to solve for missing values in our equations. So if you're trying to find the best fit, first of all, graph. And so that would be before the transformation and after the transformation. You are looking for it to be straight. So when it looks straight, that probably is a good transformation. That's meeting your L condition. I check the R squared, and the R, because that's your correlation coefficient. So you are running the linear regression. you are doing this on the transform data and looking for a R value that is strong. So you're going to look for the R strength. You want to find the strongest one that you can find. And that then you're going to be checking the the residuals, and that would be also looking at your E and your N for that. Of course, I do all these checks after I feel like I've seen something that looks straight and has a good R value. So, and now we can find that we have the residuals. They'll automatically be stored, and we can look at them and check our equivariance, and we can check for nearly normal using those right there. Okay, and then we want to check the standard deviation of the residuals, because you want your S to be as small as possible, because that is your prediction error. Possible. And that, of course, has the same units as Y, and that would just mean that your prediction error is as small, whoops, I bet you can't see that, as possible. All right, and then when you feel like you have the best transformation, just go with it. So we're going to do that for this next page. I'm going to show you how I might run through this and find out what's the best prediction. Okay, so what we have here is we have a fishing tournament. They want to be able to just put these fish into, like put the length into the into a into an equation, and then automatically come up with the weight of the fish. So they're trying to come up with a model that uses the fish's length, which is easier to measure because you can put them on next to a ruler instead of having them flopping around on a scale, so you can find out the weight of the fish. Okay, here's all this data in my calculator. So I have, if I graph it, if I go into stat plot and I turn on this stat plot, and I look at L1 to L2, zoom 9, you can see that there is a curved pattern. So when I do L2 versus L1, because remember, Y comes before if you're using the word versus. Okay, what we saw was a curve. So then right away, I'm not going to even run that, but why don't I try something like, what if I try doing what if I cube the L2 and I go versus L1? Okay, so let's try that. So I'm going to go into stat, edit, and let's say that I take my L2 and I cube it. Okay, so I get some numbers, and now I try this again with that list. Now changing this L2 to L3. So this is guess and check right now, so this is going to be a little painful, but it's just what I have to do. That actually ended up being more curved. So that was going in the wrong direction right there. That's in the wrong direction. So as well, I would have seen this. Again, it would have been also curved, but I'm not even going to bother trying that. Okay, so this did not work at all. Guess and check. So now I might change my mind to, why don't I take my L2 versus, and why don't I cube my L1? So let's see, I could try that. Edit, go into here, take my L1, and I'm going to cube that. So let's see here. Now that means that this, which is now an L3, that's going to be my x-axis, axis. So when I go into here, into stat plot, I need to say it's now L3 versus, or or L3 and L2. So, and I'm going to have to zoom 9 again. Okay, that's looking pretty straight. So, and I jumped right to the cube because I knew that this is going to end up being something to do with cube. If you had done this with L2 versus L1 squared, you would have seen it's not going to be quite as high of an R value as what we're going to get right now. But right now we see that it's straight just from overall appearance, but let's look at what the R value is. And so let's run that. And we have to make sure that when we go stat calc, and when I run my linear regression, I need to remember that it's L3 that is my X values and L2 is my Y values. So there's that. So maybe like instead of using versus, if I wanted to say it like this, L1 cubed and L2, then that might make it a little clearer what's going in first. So let's calculate this, see how it goes. And okay, my diagnostics aren't on, so I'm going to go to catalog, alpha D, turn on the diagnostics. This is kind of annoying, but so turned on the diagnostics, and then I can just go enter, and it'll bring it back up. Okay, so that gave me, when I did my L1 cubed in the X value and my L2 in the Y value, I got an R of 0.997595. Okay, so that's that right there. Okay, so then just for the sake of it, when you see something that looks pretty good like that, you may want to, and you wouldn't be wrong to just go with that. Go with what you have right now and go with it. But you might try this and the cubic root of L2. This would just to see if it was a little better. And so I'll go to stat, edit, and I'm going to, and I just kind of keep track here of what I've tried and what kind of the results were when I tried it so that I can kind of keep track. And so let's see, let's take my L2 list and raise it to the 1/3, which is the cubic root, and then go down. And so then now I have to take my L1 list and so going to stat plot, L1, L3. So it's really important to keep a track of which thing is the X and which one's the Y. Zoom 9. And that also looks pretty straight. But then what's the R value for it? So let's go into there and stat calc linear regression. Okay, where was X? X is in L1. And Y is actually in L3. And so then let's see here. We will go down here and hit calculate. And that gave me just a slightly better R value. Slightly better. So this to me seems like the best model from the ones that I've tried. So we just keep trying them and seeing when we find one that seems to work. This one being curved, with something curved, like a lot of times we think of them as being logarithms, so you could have tried some logarithms as well. And I will do that on the next pages, but this is the model that the book went with. So now we can write down what we have. I write the equation, being mindful of what I did. I took the cubic root of the weight. So I took that L2 list and I took the cubic root of it. And that was my Y. So the cubic root of the weight can be predicted, notice the hat, can be predicted by the equation. Here's my y-intercept, negative 0.0220399 plus the slope of 0.246616, and then in here we would put in the length. I think there's something wrong with my smartboard. Put in the length. And so that would be, and the weight in this situation was going to be in grams, and the length in this situation is in centimeters, just to make that clear. And so then we could use this model to make a prediction for, let's say, for example, if we had a fish that was 30 centimeters long, that would be appropriate for within our data. And we could make a prediction of what the weight would be. And so I would put in cubic root of the weight will be 0.0220399 plus 0.246616 times 30. And then we have the model spit out the number, punch that in the calculator. So the cubic root of the weight will equal 7.37656. Okay, and then now knowing that that's the cubic root of weight, we have to use our algebra skills to solve for the actual weight. So we're going to have to cube this side, and we're going to have to cube this side. And so that will give us a weight, because the cubic root and the cube will cancel. So my weight predicted in grams will be 401.3 grams. So the predicted, make sure you say estimated or predicted, because it's not going to be perfect. It's just the model saying the weight of, the weight, I have to write the word weight. The weight of a 30 centimeter fish is estimated to be 401 grams. And then if we had slight extrapolation, we would acknowledge it but potentially use it. We could also put a weight in and solve for the length. We could do that. Now, the last thing that I did neglect to do, but I'm going to do it now, is to just go through the linear. And so I'm going to do that on my calculator. And in this, I would be looking at, for my L, I would be looking at my graph where I have my length and I have my cubic root of the weight. I'd be looking at that for it to be straight, which we did look at that already. We also saw on that the R for that was a 0.9988, something like that, and that it was straight. The independence and random condition, I would say that 20 fish is going to be less than or equal to 10% of the fish. Okay, we're going to do this nearly normal. I am going to go to the calculator to look at that. Use the residuals in the calculator, and I'll show you that. And then that's going to be our N. It's also going to be our E. So I'm going to go to the calculator and do that. And then, of course, that we had a random sampling of fish, we would need to check that too. So I think these fish are really only going to describe this particular water body wherever we're having these fish. But let's go to the calculator and just quickly look at how we would check the nearly normal and the equivariance. Okay, so back to my calculator, and this, when I generated this equation, it actually in the list, If you look down here, it actually generates the residual list. So if I want to go into stat plot and just look at those lists, think about what you need to graph. You need to graph the histogram of your residuals. Now to call in that name, hit second and stat to get to the lists and just click on resid. Look at that. So much easier. Gosh, if only somebody told us this before. Zoom 9. And there you go. That is looking spot on symmetrical, doesn't it? Okay, now let's go to the next one. So that was our histogram, but let's go in there and turn it into the box plot just to make sure we don't have any outliers. And zoom 9. Great. No outliers. Now let's go into our stat plot and look at our normal probability plot. Or sorry, scatter plot of the residuals, I mean. We do want to do the normal probability plot at some point. Well, maybe I'll do that first. Normal probability plot. Boom, boom, boom. Zoom 9. Looking really straight. So that's looking great. Now I just need to do the equivariance. So I've established normalcy. Now I just need to check the equivariance. So this can be a little tricky though, because when you're plotting your scatter plot, and you need your residuals actually on the y-axis, and you need to remember that if you transformed your x-axis, make sure you move to wherever the new x-axis is. But what did you use when you ran the linear regression? And we actually used the L1, so that makes it a little easier because we had run L1 versus L3, or sorry, L3 versus L1, because we had done x was in L1, y was in L3, which was the cubic root of the weight. Anyway, so let's bring in the residuals. So much easier like this. I didn't even have to write the equation into anything. Zoom 9, and maybe a little bit of clustering here. Somebody might be able to say that there's a little bit of a curve to this, but as I trace along here and look at how far off these residuals are, see that I can see and how far off you are in the y direction, that's really small. And that speaks to that standard error of the residuals. And as I mentioned earlier, this particular model has a really small standard error of the residuals. This model, the standard error of the residuals was only 0.12, and that would be cubic grams, because it's cubic root of grams. But so this is a pretty good model, I'd say, for the purposes of just predicting fish. I mean, it's not like anybody's going to die if the fish are not exactly the right prediction. But anyway, next video is going to have some logs in it.